In this session, we'll be discussing about energy transfer in a progressive wave as such. So, in a progressive wave, there are a series of particles which keep transferring the energy to one another. So, when discussing the differences between a progressive wave and the stationary wave, you would have been told that in a progressive wave, there is an energy transfer. So, we need an expression for this energy transfer. So, that is what we'll be discussing in this class. So, when you speak about energy is divided into kinetic energy and potential energy. So what we'll be doing is we'll be deriving an expression for potential energy. We'll also be deriving an equation for kinetic energy. And with that, we'll find the equation for a total energy. So let us get into the derivation straight away. Yeah, so I presume my screen is visible to you. Let us go on in discussing. So energy transfer, what we'll be discussing today is energy transfer in a progressive way. Right. So let's first see about displacement. Okay. So you would have seen, you learned for a sine wave, the displacement y is given by a sine omega t, where omega is the angular frequency. Or you could write omega is equal to 2 pi n, where n is the frequency. So this equation now becomes a sine 2 pi n t. Or frequency n, we know, is equal to velocity by wavelength, v by lambda. So this equation would now become y is equal to a sine 2 pi v by lambda into t. Now let us look at this wave. I have a wave here. I'm taking a transverse wave because it is easier to visualize. So I have lots of particles in this wave. Lots of particles. So there is an energy transfer. So once this starts vibrating, this transfers energy to this. Then this will transfer energy to this. This goes on and on between all the particles. Let me consider a particle at a distance x. Let me also consider the wave is moving at a velocity v. So this particle will start vibrating at a time much later than this. And the time it starts to vibrate will be determined by the distance traveled and the velocity of the wave. So now this equation, I could modify it as y is equal to a sine 2 pi by lambda vt minus x, giving you the distance between the origin and this vt minus x. This is my equation for displacement. So having this equation, I am now going to find out the expression first for kinetic energy. I shall find the expression for kinetic energy, and you know kinetic energy is equal to half m v square. Let me start with finding v. V is equal to dy by dt, or you could say d by dt of a sine 2 pi by lambda vt minus 6, right? So your velocity now becomes, so what is the coefficient of t? Coefficient of t is 2 pi v by lambda. So that comes here. 2 pi v by lambda comes here. Then you write a cos. Differentiating sign will give you cos. A cos 2 pi by lambda vt minus x. This is the expression for velocity. Now, you know density. Density rho is equal to mass per unit volume. We all know this. So unit volume, let me take V as 1. So I shall have here mass divided by 1, or I can write rho is equal to m. Now let me substitute this and this in my equation for kinetic energy. So my kinetic energy now becomes half, instead of m I am putting rho, into 2 pi v by lambda a cos 2 pi by lambda vt minus x whole square, because it is v square. So what would our equation for now kinetic energy now become? Kinetic energy is equal to half rho I'm squaring this, so that would become 4 pi square v square a square by lambda square. This would become cos square 2 pi by lambda Vt minus x. Obviously, this 2 will get cancelled with this. So our kinetic energy equation is now going to be 2 rho pi square v square a square by lambda square cos square 2 pi by lambda Vt minus x. I'll call this my equation 1. So I have an expression for kinetic energy. Let us now try to find out an expression for potential energy. So when does a particle possess potential energy? Due to its displacement from its position. And in a way, at the mean positions, the displacement it is 0, and at the extreme positions, the potential energy is maximum at the extreme positions, and at mean position is 0. So the work done in taking it from a mean position to extreme position is to be considered. So first, let us take the work done per unit volume. So let us say work done. I'll write it this way in a minute. So I shall write now work done is the amount of force required in taking it through a distance. So F is the amount of force through a distance dy. First, I need to find an expression for F. So we all know that force F is equal to mass into acceleration. M is rho that we already assigned. I need to find acceleration. How can I find acceleration? You know acceleration is equal to dv by dt. I already have an expression for v. So A is equal to d by dt of 2 pi a 2 pi av by lambda cos 2 pi by lambda vt minus x. Where is this fellow? Here. 2 pi va by lambda cos 2 pi by lambda vt minus x is v. So I need to differentiate this. So what will I get? I already have 2 pi v by lambda. Again, another 2 pi v by lambda will come here. So what will I get here? 4 pi square v square by lambda square a. A will only be a. A is not a coefficient of t. So when you're differentiating cos, you're going to get sine. So what do we get? Sine 2 pi by lambda vt minus x. Of course, cos when you're differentiating it is minus sign. So you put the minus sign. But I am only speaking about energy transfer. So I am not actually worried about, I'm only speaking about again a total energy. So which means I'm not worried about the minus sign. So I only need the magnitude of acceleration. So I will substitute the magnitude of acceleration here and also substitute for m. So force is equal to, which is m is rho. And what is this A? A is 4 pi square v square by lambda square a sine 2 pi by lambda vt minus x. But a sine 2 pi by, okay, 2 pi by lambda vt minus x is what? Y. So I can write F is equal to rho 4 pi square v square by lambda square into this entire thing is Y. So now work done is equal to F into Ty. So this is equal to rho pi square v square lambda square y into dy. This is the work done in moving this. So having this work done, the total work done in displacing it from the mean position, I told you, gives you the potential energy. So to find the potential energy of the wave, potential energy is equal to, I will get it by integrating this. So what will I have? Rho 4 pi square v square by lambda square integral 0 to y of y dy. So you will now get potential energy as equal to rho 4 pi square v square by lambda square, right? So this will be, when you integrate, it will be y square by 2. So 2 and 2 will get cancelled. I get a 2 here, and I'm also going to replace for y here. So what will I get here? Potential energy is equal to 2 rho pi square v square by lambda square. I'm going to replace for y square. Y we know we have seen as a sine 2 pi by lambda vt minus x. So I have y square here. So what will I have here? A square sine square 2 pi by lambda vt minus x. This is my potential energy equation. Let us straight go into a total energy. We are making things now simpler. So total energy we know is equal to kinetic energy plus potential energy. So let us first write the kinetic energy component and then write the potential energy component. So you will have 2 rho pi square v square a square by lambda square cos square 2 pi by lambda Vt minus x. This is the kinetic energy. So what is the potential energy? Same thing, 2 rho pi square a square v square, right, by lambda square sine square 2 pi by lambda Vt minus x. I hope I'm right. I have this 2 rho pi square v square a square by lambda square. Yes. So what do you get here? 2 rho pi square v square a square by lambda square, take common, cos square 2 pi by lambda Vt minus x plus sine square 2 pi by lambda Vt minus x, because this is common. So you know cos square is like cos square theta plus sine square theta, which is equal to 1. So total energy is equal to 2 rho pi square v square a square by lambda square. So your average energy is going to be what? Average kinetic energy is this divided by 2. And your average potential energy also is going to be this divided by 2. So now this v square by lambda square, I can write it as 2 rho pi square n square a square, because you know v by lambda is frequency m. And finally what we have is, I just have one more step to go. Energy transfer. We have the energy. So what is the energy transfer? Energy transfer is equal to total energy into velocity. So what is our total energy? 2 rho pi square n square a square into this is our total energy. Okay. So what did we do? We found out the kinetic energy. We found out the potential energy. We added them to get the total energy. That multiplied by velocity gave us the energy transfer in a progressive way. If there are any doubts, please post it in the comment section.